Now next topic, that is torque, which is also known as moment of force. Now see, in linear motion we studied about the physical quantities like linear displacement. Exactly like that, here in rotational motion we have the quantity angular displacement. That is analogy. Now in linear motion we have linear velocity. Here in rotational motion there is analogy of linear velocity with angular velocity. Then linear acceleration have analogy with angular acceleration. Like that, force in linear motion and torque in rotational motion have the analogy. Means force is the physical quantity which one is responsible for the change in linear motion. Exactly like that, torque is the physical quantity which one is responsible for the change in rotational motion. Okay. Now let's define the torque. Okay. See, here this torque, that is also known as moment of force. It have analogy with force that I already mentioned. Okay. Now suppose as shown in this figure, we have a particle P at position R with respect to the origin of Cartesian coordinate system. And now suppose force acting on this particular particle, that is in the direction as shown in the figure here. Now here if we extend this position vector R, then we can say here the angle between R and F. When you take angle between two vectors, you have to think both the vectors from the same origin. So if we, in other words, we can say like this, if we place position vector from this point, then the angle between R and F, that is theta, that is this one. Okay. Now see here, torque is defined as the vector product of position vector R and force F. So torque tau, this one is pronounced as tau, that is equal to vector R cross vector F. Again here, the direction of torque, that can be represented with the help of right hand screw, because on right hand side that is the vector product. Now here, angle between R and F, that is theta. So magnitude of tau, that we can write RF sin theta. But see here, now if we take the line of action of the force, line of action of the force means we have to imagine a line passing through the vector of force. Then draw a normal from the origin to this line of action. Draw a normal. So this particular angle, that will be 90. This angle is theta. So this one is also theta. Now R, that is the hypotenuse. So we can say this opposite to theta, this side, that is represented as R sin theta. So if you arrange this one as tau equal to force F into R sin theta, then R sin theta is what? R sin theta, that is nothing but the perpendicular distance of force with respect to this reference point. Reference point, that is the origin. That is the perpendicular distance of force. So here we can write torque tau, that is the magnitude of force into perpendicular distance of force with respect to reference point. Here its SI unit will be Newton into meter, right? It is also known as moment of force. So remember this word also, moment of force and torque, that is one of the same thing. So dimensional formula, that will be m1 L2 T minus 2, because Newton into meter, that you represent as joule also. So dimensional formula, that is like work. Clear to all of you? Now here, if from this equation you can understand this thing, torque tau, that is depending on R, F and theta, the angle between R and F also. If R is equal to 0 or F equal to 0 or theta equal to 0 or 180 degree, in any one case your tau is 0, right? Now here this you can easily understand. Suppose you want to open or close the door, then when you hold the handle, at that time if you apply the force parallel to the door or in the opposite direction but parallel to the door, then door will not open or closed. You have to exert some force on the handle at some angle, as well as that particular handle, that is at as possible as at maximum distance from the rotational axis of the door, right? So with the help of this type of day-to-day example, you can understand this thing easily. Clear to all of you?